is my demo. For each technique, the recommender gives top 5 gains recommendations. And I created 3 different techniques, and including a content-based results, the item-based result, and the LS results. And for each user, I can give them the different recommendation results. So that's the basic concept. So go back to our slide. Okay. So the recommendation system pipeline start from collecting data, regulating data ETL pipeline, building model and tuning model, and deploy model into production. For each stage, I will not talk about this in detail due to limited amount of time. I will only show the result and focus on the theory behind different techniques. Okay, so where's the data from? Simply speaking, I got real-world data from Steam API using Python library code requests. And Steam provides a way API interface to allow users to collect data through making API requests. So basically, this is what we got. The data looks like messy, and after we manipulate this data, it looks like this. We transform it into the format of the data frame for the following process, including storing them into a MySQL database and modeling. So to connect Python to MySQL database and store the data into MySQL, I use a package called SQL Alchemy. This package helps me connect the database through entering these parameters, including username, password, host, database, and the data can be installed into a MySQL and accessed from MySQL whenever I need this data. And I can use the query technique to get data like I want. It's like how we do in MySQL. Here, instead of querying data in MySQL database, I query data in Python and get the data from MySQL. So it's basically the ETL pipeline. I extract data from one source and transform the data to load another source. So now we have this data we need. Before we build a recommendation model, let's dive into the features. These are data we use to create a recommendation system, including item users, and time users have spent on games. And we found there's a problem about the feature playtime forever. We can see from this table, the maximum playtime of each game is hugely different. So from 1 to 170K. So if we directly use playtime data as a rating, the model will recommend users those games which have large maximum playtime. For this reason, we transform the playtime on the same scale by using cumulative distribution function of playtime. So we can see the cumulative distribution function here, and we transform from playtime to the new rating from this table. So once we have our data prepared, now it's time to build our recommendation system. There are 3 different techniques that build recommendation system. The first is item-based collaborative filtering. The second is content-based filter, and the third is metric factorization. And one of the technique is alternating least square. So what is the item-based collaborative filtering? It's a technique calculate the similarity between the items and recommend users similar items based on user's preference. From the left graph, we can see the 2 girls both buy the 2 product, grape and watermelon, and we can see this guy also buy the watermelon. So we will recommend this. We can recommend the grape to this guy. So we can see. The similarity between the item is higher. We will recommend the user the items that with a higher similarity. So if it's not clear, there's another example. When we go to Amazon, each time after we buy some product, Amazon will recommend similar products. They will say other people also buy this and recommend you to buy this. So it's a basic concept of item-based collaborative filtering. And the metric we are using is cosine similarity. The angle between A and B we call theta. If theta is larger, cosine theta will be smaller, and then similarity between A and B is smaller. So cosine similarity of A and B is given by this stuff of the equation. Okay, so I think if you are familiar with cosine function, the top of this fraction is the dot product of A and B, and then bottom fraction is the distance between f vector to 0 multiply the distance between vector b to 0. So that's our basic concept of how to use item-based filtering. So, however, there are two shortcomings of item-based filtering. We can see this graph, the left graph, the popularity bias that show me the count of game being played. We can see only a small fraction of game have a lot of user interactions, while a long tail of games don't have. From the business perspective, high-frequency items tend to be relatively competitive items with little profit for the merchant. On the other hand, the lower frequency items have larger profit margins. So there are a lot of so that's one problem of item-based collaborative filtering. And the other problem is cold start problem. There are a lot of unknown values in the cell of the matrix. So recommender fails to recommend new or less known items because items have either none or very little interactions. So to overcome the difficulties of item-based filtering, we propose another method called content-based filtering. This technique recommends items to user based on the content of the item a user has watched or liked. For example, if I like to play the games related to bird, the recommender will recommend me the games. So the input we are using is the short description here. So it just depends on the content of description. So, and then we will use the information retrieval. It's one of the technique that can quantify this text into a number because the machine only accepts the number. And then we use the same metric to calculate this similarity between the items. We use a cosine similarity to calculate the similarity between different games. So for this technique, the advantage is it can solve the cold start problem. There's no popularity bias. But the disadvantage is it's easy to pigeonhole the user. For example, if I like to play the RPG game, the recommender will recommend me the similar game over and over again. So here I will introduce another technique. So this is called matrix factorization. Assume we have a matrix where rows represent user and columns represent items. In our case, it's games. So basically, users watch users play some games and give the ratings. And here is how long they play on the games. So, but how about the missing cells in the matrix? We are going to fill in those unknown cells with predict ratings, and then depending on this rating to give a user the recommendations. So we have a rating matrix, user matrix, and item matrix. And so how does this matrix describe typical users and typical movie help us to predict rating? From this equation, we can see that item matrix and user matrix transpose are both the factors of a original rating matrix we started with. So if we have M, we have U, we can reconstruct our matrix. And if our matrix is missing some ratings, and if we have N and U, we can fill all those blanks in our matrix. That's why we call this matrix factorization. We describe our training data in terms of smaller matrices that are factors of the ratings we want to predict. So in this question, there's also a sigma metric in the middle that we haven't talked about. It's just simple diagonal metric that only serves to scale the values we end up with into a proper scale. You could just multiply the scaling metric into N or U and still think of R as just a product of two metrics if that makes it easier to wrap your head around it. So we could just reconstruct R or the one by multiplying these factors together and get rating for each combination of user items. Once you have this factor, you could just predict the rating for specific user item by taking the top dot product of associated row in U and for the user and associated column in NT. Here is item matrix for the item. And that's just how matrix multiplication works. For example, if we want to predict the arrow, the rating, predict the rating of the arrow and W column, we'll calculate, we'll treat this as, each rating can be described as the dot product of, each rating can be described as arrow and the W column. So we just calculate arrow and W column, we can get the rating for the arrow W column. So that's the basic idea of how metric factorization works. So, and we can treat this as a minimization problem. Every time when we do this, and then we can see that if it's closer to actual rating, and then we will run this. So how to solve this minimization problem? FH Spark, for example, uses a technique called alternating least square, or LS, to solve minimization problem. So there are 4 steps in this algorithm. The step 1 is initialize a matrix by assigning the average rating for the movie as a first row and small random number of.
Yes. I don't mean to interrupt. I don't know if you're looking at the chat window. There's basically just maybe 1 minute or so left.
Sorry?
Oh, I don't know if you're looking at the chat window where I'm putting in the time. There's roughly like a minute and a half or so left. I just wanted to alert you.
Okay, so how many minutes I have run?
We're 13 and a half minutes right now.
Okay, 30 minutes?
Yeah. So you have maybe like 1 minute.
Let me finish in 1 minute. Yeah, so in this algorithm, it's very easy. In step 1, we initiate a matrix, in item matrix for random values. And then step 2, we fix N and solve U by minimizing object function. So here we have item matrix and we have a rating matrix. We can calculate user matrix. And then the step 3, we fix the user matrix and calculate item matrix again. So for each iteration, we update the user matrix and item matrix. So repeat that until the stopping criterion is satisfied, which means the error is converged like this. So in this case, in the number of 2 iterations, our learning curve is converged. So okay, I think I just stop here.